So the fundamental K for a knot is first of all, it's a magma, right? And its elements are the arcs of the diagram. Um, but the elements are actually usually more than just the arcs. They also include any word that we can write out using the arcs and the triangle operation, right? So whatever my arcs are and anything that I can get by triangling those arcs with one another, those are going to be the elements in my fundamental K. And the relations, the simplification rules in the fundamental K are just given by the equations, the relationships that we would get at each of the crossings in the diagram. So let's do an example together on a knot diagram. So here's a diagram of what's called the figure 8 knot, 4-1. It is the only the only knot with 4 minimum crossings in it. And I just sort of sketched up here are the 3 K rules that we know every K has to satisfy. What I want to do is use this definition of fundamental K to try and build at least a portion of the operation table for the fundamental K of this knot. So what that means is that I know, first of all, that the 4 arcs in my diagram, those are going to be some of the elements of my fundamental K. So I'm going to put them in here, W, X, Y, and Z. W, X, Y, and Z. So now I need to figure out, what do I get, for example, in my operation table when I do W triangle W? Well, we have a K operation for that, right? W triangle W we know is guaranteed to be W. X triangle X is guaranteed to be X. Same thing with Y, same thing with Z. So we've already filled in 4 of our entries inside of my table. All right, so let's keep it going. If I look at one of my crossings, let's say I look at this one right here. This is a crossing at which the highways X and Y come together under the bridge W. And so that's telling me that X triangle W is going to give me Y. So that's one relationship that I can get from this part of the diagram. X triangle W is equal to Y. And so in my operation table, I can fill that in right here. X triangle W is going to give me Y. But then, because these are two-way streets on this knot diagram, we could also have considered Y to be one of my highways and W to be the bridge, and X must then be Y triangle W as well. This is one of the nice things about working with Ks, is that each of the relations is going to give me 2 different entries in my operation table. So Y triangle W is going to give me X. So I have now 2 more entries in my operation table. We'll just take a quick run around the other crossings in my diagram to get some more relationships. So over here, Y is my bridge, and Z and W are my highways. So Z triangle Y is W, and then conversely, W triangle Y is Z. So I can fill in 2 more. W triangle Y is Z, Z triangle Y is W. Then we'll come down to here where the bridge is Z, and the others are W and X. So X triangle Z is W, and W triangle Z is X. So that fills in this entry, and it fills in this entry. And finally, at my 4th crossing, down here, the bridge is X, and the highways are Y and Z. I hope I have this right. So Y triangle X is Z, and Z triangle X is Y. Triangle X is Z, and Z triangle X is Y. So now that I've gone through all 4 of my crossings in my diagram, I've filled in as many places on this operation table as I can. And what you'll notice is that we don't have a good answer, for example, for what is W triangle X, because there's no place on this diagram where X is the bridge at a crossing where W is one of the highways, right, going under the bridge. And so what that means is that really W triangle X is a new element in my K. It's something fresh, something I can't necessarily determine just from the information that's there. So it becomes another element, W triangle X. And then we would try to work our way out from there. Since it's an element in a K, when I triangle it with itself, I'm going to get itself again. So W triangle X ends up over here. Meanwhile, W triangle X triangled with X needs to give me something special. right? According to my second K property, W triangle X has to give me W. But then we're also going to get potentially, potentially more elements inside of this operation table, and it's going to keep growing. What we hope to happen, and there actually is there's an infinite many different knots for which this does happen. We hope that eventually we run out of new elements that we have to add in this process, and our K can have a finite number of elements in it. But as you can imagine, it would take potentially some shrewd uses of these three properties in order to demonstrate exactly how many elements are in this fundamental K. But by the time we got there, we would have this big algebraic structure that encodes sort of all of the information that we could hope to encode about this knot diagram just using an algebraic structure. Y triangle Z, and so on and so on. So this one is kind of challenging because we had 4 crossings to work with, and we quickly realized that there weren't enough crossings in our diagram to be able to specify the values of all of these triangle operations. We needed to start to add some more new things in. So what I'd like for you to do to wrap things up for today with your team is to take about 10 minutes or so and just try this process that we just did, but try it with the simpler knot. Try it with the trefoil. If you just take the trefoil and label its arcs X, Y, and Z, see if you can go through this process and come up with an operation table for the fundamental K of the trefoil. See if it's, as advertised, simpler than the example of the 4-crossing knot, the figure 8 that we just did. The great thing about the trefoil is that in constructing its fundamental K, we don't have to work too hard because we have enough relations between idempotents and between the pair of relations that we get at each one of the crossings in this to be able to fill in all 9 entries of the operation table without discovering any new elements in the process, right? We use idempotency to fill in the diagonal. X triangle X is X, Y triangle Y is Y, Z triangle Z is Z. And then we use the crossings to fill in the rest. For example, Y triangle X, this is, I heard one of your groups pronounce it this way, and I like it, Y under X. So we look for a place in the diagram where the Y arc passes under the X bridge, and that's right here. And when the Y arc passes under the X bridge, it emerges as the Z arc. So Y under X gives me Z. Z under X gives me Y. X under Y gives me Z. Wait, let me make sure that's right. Here is X under Y. It emerges on the other side as Z. Z under Y gives me X. X under Z gives me Y. Y under Z gives me X. And so in the process, we had enough information from the 3 crossings and from the idempotent property to be able to fill out the whole table. And so the fundamental K of the trefoil knot has only 3 elements, X, Y, and Z, and its complete operation table is shown right here. You'll notice in fact, one of your groups did notice that that's the same operation table that was activity 4.1.8. Show us whether this magma forms a K, and it does. It turns out that there is really only one way to make a K that has 3 elements in it. But that's meaningful in a different way, and this is where I want to close by tying this back into the idea of coloration. So remembering that the way that we could tell about 3 coloration was by assigning the color of the bridge arc to be the average of the colors of the highway arcs that are going under it, right? So we could use a K on Z modulo 3 using this K operation. So let's see what that would look like. So this is called the 3-element Takasaki K, named after the person who coined the word K in the first place. So the Takasaki K for Z modulo 3, integers modulo 3, is just, it follows the equation X triangle Y is 2Y minus X modulo 3. And the elements in that Takasaki K are just the elements of Z mod 3. In other words, the remainders mod 3, 0, 1, and 2. 0, 1, 2, 0, 1, 2. And if we go through this process, we can construct the operation table using this operation for this particular magma. And again, it's easy to check that this is that this operation satisfies the idempotent property, right? X triangle X is going to be 2X minus X mod 3. That's the same as X mod 3. So 0 triangled with 0 is 2 times 0 minus 0, 2 times 1 minus 1, 2 times 2 minus 2. So we get the diagonal once again. 0 triangle 1 is going to be 2 times 1 minus 0. That's going to be 2. 0 triangle 2 is 2 times 2, which is 1 mod 3 minus 0 is 1. And then we continue. I'll sort of speed up this process a little bit here to save a little time. And so the Takasaki Kei, the Kei that I get out of this mod 3 arithmetic using this operation, looks like this. Well, what do you notice about these two Ks? I guess I'll say, what is the relationship between these two Ks? At the level of algebraic structure, what do we see? We can come up with a relationship between these two Ks by associating 0 to x, 1 to y, and 2 to z, and observing that the 0, 1, and 2 in this Takasaki Kei interact in exactly the same ways that respectively the x, y, and z did in the fundamental Kei of the trefoil. And so what we get is a function. It's called a K homomorphism. In this example, it's actually a K isomorphism. From the fundamental Kei of the trefoil into the Takasaki Kei of Z mod 3. The two are the same. And so what that's actually telling me, because we know that this Takasaki Kei is set up in such a way that the bridge is the average of the unders, and because it's mod 3, we know that that encodes tricolorations. So the fact that I have a K isomorphism here is telling me that my knot has a tricoloration. 3-coloration. So this is what I mean when I say that the fundamental Kei of a knot kind of contains all the information about colorability inside of it. All we have to do is take the Takasaki Kei on however many colors we're trying to use on the one hand and see, is there a K homomorphism or isomorphism, better yet, from the fundamental Kei into that Takasaki Kei. If there's an injective homomorphism, then there is. Right? If we can kind of find a copy of that coloration Kei, the Takasaki Kei, inside of the fundamental Kei, then that means we have one of those colorations that we would want to have. And in this example, it's kind of the easiest to see just because this K is really small, right? The fundamental Kei has only 3 elements, and the Takasaki Kei has only 3 elements that behave in exactly the same way that the arcs in our fundamental Kei behaved. So you might imagine that if we wanted to do this with the fundamental Kei of the figure 8 knot, that there might be a little bit more to do. I believe, and don't quote me on this because I haven't finished this calculation for a little while. This might be one thing I ask you to explore a little bit over the next few days. I believe that the fundamental Kei for the figure 8 ends up having, I think it's 8 elements instead of 6. And so one of the questions that we might ask is, well, if it has 8 elements, is it even possible for us to construct a K homomorphism into the 3-element Takasaki Kei? Or are we going to have to use a 4-element Takasaki Kei? Because we know it's going to be 4-colorable because it only has 4 arcs. So there must be some K homomorphism from the fundamental Kei of this knot into the 4-element Takasaki Kei. But actually figuring out what that is, I mean, we could figure out what that 4-element Takasaki Kei actually looks like, and then see if there's a way to kind of make it sort of find that algebraic structure inside of our 8x8 operation table of the fundamental Kei. But the idea is that this fundamental Kei is going to be the strongest algebraic invariant that we're going to see in our course for knots. The only thing that a fundamental Kei can't do is it can't tell the difference between a knot and its opposite, the reverse. This would be the knot that we would get by reversing all my crossings from overs to unders. Okay? The mirror image, if you like. The K can't tell the difference between a knot and its mirror image. And the reason for that is that we don't have we have a two-way street going on here, right? If we relaxed that, and if we made all of our highways one-way highways, then we would have to rethink our K operations just a little bit, because we wouldn't have the symmetry that the K operation has with the 2 under arcs. We would have an incoming highway and an outgoing highway and a bridge. So all 3 of those would be different. But we wouldn't have to do too much other work, because we would still just need the 3 Reidemeister moves. If we do that, the K operation turns into what's called a quandle, which is my favorite word probably in all of knot theory. A quandle is just a K that you obtain by using an oriented knot diagram instead of an unoriented knot diagram. And because adding that orientation gives us the ability to tell the difference between a knot and its mirror image, because then we'd be reversing the traffic flow in the mirror, it turns out that the fundamental quandle of a knot, which is what we would get by doing this process that we did for the K, but using the quandle operations instead. So we have to have an orientation on the knot. That fundamental quandle is the only, as of right now, today, the only known complete invariant for knots. So once you build the fundamental quandle, it's going to be some big, nasty algebraic object. Even this fundamental K for this four-crossing knot is already pretty big. So as you can imagine, it gets unwieldy pretty quickly. But the fundamental quandle, because it's a complete invariant, if you give me two quandles that are the fundamental quandles of knots, and those quandles are different, then we knew for sure that the knots had to be different. But also, any two different knots will necessarily have different fundamental quandles. So it is a complete invariant for knots. And because it's a complete invariant, homomorphisms, quandle homomorphisms coming out of the fundamental quandle are how we can find the lesser invariants. So we can find coloration invariants by homomorphisms out of the fundamental quandle. We can find things like crossing numbers and stick numbers and bridge numbers and all the other invariants that we've talked about. Any other invariant indeed that we can define on knots. There exists some way to construct it as a homomorphism out of the fundamental quandle. So that is the Rosetta Stone for knots. And so we can construct it using the same process that we did now, just by using the quandle operations instead of the K operations. And to give the game away just a little bit, the only thing that really changes for quandles is that type 2 Reidemeister move. That's the only one that just changes a slightly little bit to kind of give us a notion of cancellation in the way that type 2 move did. But otherwise, it's more or less the same as the procedure that we just did.